Hey everyone, welcome back to my YouTube channel, where we break down complex engineering concepts into simple, easy-to-understand lessons. Today, we're diving into something that every aspiring engineer or physics enthusiast must know, the fundamental concepts and principles of mechanics. When we talk about mechanics, the study of motion, forces, and energy, we're really standing on the shoulders of giants. Let's take a quick tour through history and meet the minds who shaped the science of mechanics. First up, Aristotle, the famous Greek philosopher from 384 to 322 BC. He may have gotten some things wrong, like believing heavier objects fall faster than lighter ones, but his writings sparked centuries of inquiry. Aristotle tried to explain motion and change, laying down some of the earliest recorded theories about how objects move. For a long time, people believed, following Aristotle's idea, that heavier objects fall faster than lighter ones. It seemed obvious. Drop a rock and a feather, and the rock hits the ground first. But this is actually misleading. In the late 1500s to early 1600s, Galileo Galilei challenged this belief with experiments and observations. According to stories, and likely some myths, he dropped objects of different masses from the Leaning Tower of Pisa. What really matters, though, is his use of inclined planes to slow down the motion of falling objects so he could carefully measure and observe them. What did Galileo discover? When you remove or minimize air resistance, all objects, no matter their mass, fall at the same acceleration. This acceleration is due to gravity, which on Earth is about 9.8 meters per square second. In other words, a rock and a feather fall differently in the air because the feather encounters much more air resistance relative to its weight. But in a vacuum, no air, they fall side by side, hitting the ground at the exact same time. This concept was later confirmed in modern times, famously during the Apollo 15 moon mission, when astronaut David Scott dropped a feather and a hammer on the moon, which has no atmosphere, and they hit the surface together. Why was this a huge turning point? Galileo's findings shifted the way scientists think about physics. Instead of relying on assumptions or what seems obvious, experiments and measurements became the foundation of science. This work eventually paved the way for Newton's laws of motion and a deeper understanding of gravity. Then came Archimedes of Syracuse around 287 to 212 BC, a brilliant mathematician, inventor, and engineer. He gave us the law of the lever, explaining how forces balance on a pivot point. In simple terms, he showed that if you place a lever on a pivot, or fulcrum, you can balance different weights by adjusting their distances from that pivot. Think of a seesaw. A heavier person can balance with a lighter person if the heavier one sits closer to the center and the lighter one farther out. He also discovered the principle of buoyancy, yes, that eureka moment in his bathtub. The story goes like this. Archimedes noticed that when he stepped into his tub, the water level rose. That got him thinking, and he realized that an object submerged in a fluid gets pushed up by a force equal to the weight of the fluid it displaces. That's why some things float and others sink. If the buoyant force is greater than the object's weight, it floats. If it's less, it sinks. It might sound simple today, but this principle explains everything from why ships float, to how submarines dive, to how hot air balloons rise. And yes, he was so excited when he figured it out, he supposedly ran through the streets shouting Eureka, which means, I found it! Archimedes' work bridged the gap between philosophy and applied science, especially in statics and fluid mechanics. Fast forward to the 17th century, Sir Isaac Newton, the father of classical mechanics. His three laws of motion and the law of universal gravitation gave the world a complete mathematical framework to describe how objects move and interact. Newton's laws weren't just theories, they actually explained how the world works. From falling apples to the motion of the planets, his laws showed that the same rules apply everywhere. They proved that motion isn't some random mystery. It follows predictable patterns we can measure and calculate. And this wasn't just for science. His laws became the backbone of engineering and physics. They gave engineers a way to design structures, machines, and systems based on solid, predictable principles. Whether you're building a bridge, designing a car, or launching a rocket, Newton's laws are at the core of how it all works. They turned guesswork into science. In the 18th century, Jean-Le Rond d'Alembert, a brilliant French mathematician, refined Newton's ideas even further. While Newton gave us the laws of motion, d'Alembert helped make them easier to apply in real-world problems, especially in mechanics. His big contribution? D'Alembert's principle, a clever way of turning dynamic problems with moving objects into static ones, where forces balance. This principle made it easier for engineers and scientists to analyze motion, forces, and systems in equilibrium. It's like turning a moving problem into a solvable balance of forces. Thanks to d'Alembert, mechanics became more practical, not just theory on paper, but a tool engineers could actually use in design and analysis. Next, Joseph Louis Lagrange took things even further. While Newton's laws focused on forces and motion, Lagrange found a new way to look at mechanics, using energy instead of forces. He introduced Lagrangian mechanics, which reformulated Newton's laws into powerful mathematical equations based on energy principles. Why was this a big deal? Because it allowed scientists and engineers to analyze complex systems, like machines with lots of moving parts, using a single equation, instead of tracking every force separately. Today, Lagrangian mechanics is a foundation not just in engineering, but also in advanced physics, even in fields like robotics, aerospace, and quantum mechanics. It showed that Newton's ideas weren't the end of the story, they were just the beginning. Finally, William Rowan Hamilton pushed mechanics even deeper with what we now call Hamiltonian mechanics. Like Lagrange, Hamilton reformulated Newton's laws, but his approach focused on energy and momentum in a way that opened up entirely new doors in physics. His equations gave a powerful mathematical framework for understanding how dynamic systems evolve over time. Why does this matter? Because Hamiltonian mechanics isn't just about solving engineering problems, it became a key tool in advanced physics, especially in quantum mechanics, where it helps explain how particles behave at the smallest scales. Hamilton's work revealed the deep connections between motion, energy, and conservation laws. It showed that mechanics isn't just about moving objects. It's about understanding the hidden rules that govern how everything in the universe behaves. And yes, in the 20th century, Albert Einstein shook things up with his theory of relativity. Einstein showed that Newton's laws aren't the whole story, especially when you deal with objects moving near the speed of light or in super strong gravitational fields, like black holes or massive stars. In those extreme cases, Newtonian mechanics breaks down, and Einstein's equations take over. But here's the important part for us. For everyday life, engineering, construction, designing machines, vehicles, Newtonian mechanics still works perfectly. Whether you're calculating forces on a bridge, designing an engine, or analyzing a moving car, Newton's laws are still the go-to. So while Einstein expanded our understanding of the universe, Newton laid the foundation we still build on today. So whether you're calculating forces on a bridge, analyzing a moving car, or studying the motion of planets, you're applying principles refined by centuries of genius minds. Mechanics isn't just theory, it's the language of the physical world. Now we're talking about the four basic concepts that mechanics is built upon: space, time, mass, and force. These are concepts we all experience every day, yet they form the foundation of how engineers and scientists understand the world. In mechanics, space simply means the position of a point in a given reference frame. It's how we describe where something is. Think of it like plotting a point on a graph. You use coordinates to tell the exact location. Let's start with 2D space or two-dimensional space. Here, we use two axes, usually the x-axis and y-axis, to describe a flat surface like a map, a piece of paper, or a floor plan. If you want to locate a point on this plane, you just need two numbers, one for the x position and one for the y position. But most objects in real life don't just sit on a flat surface. They exist in 3D space, or three-dimensional space. So we introduce the z-axis, which measures height or depth. Now, instead of two numbers, you need three coordinates, x, y, and z. And that lets you describe any point in space, whether it's a plane flying overhead or a building on a city block. Now, depending on the situation or the diagram you're using, the x, y, and z axes can actually be interchanged. Their directions aren't fixed by some rule of nature. What matters is that they're all at right angles to each other. We just follow common conventions for clarity, like x for length, y for width, and z for height. But in mechanics, you can set them up however fits the problem best. In mechanics, defining space is everything. Without it, we wouldn't know where objects are, how they move, or even how to calculate forces and motion. Every analysis of motion, force, or structure starts with, you guessed it, knowing the position of points in space. So whether you're analyzing a simple flat structure in 2D, or studying the motion of a spacecraft in 3D, understanding space and coordinates is your starting point in mechanics. And that's just the beginning, because space connects directly to time, motion, and forces. All things we'll dive into in the next part. Now let's talk about something we often take for granted, time. But in mechanics, time plays a bigger role than you might think. Time tells us when something happens, and how long it takes. It lets us measure how fast or slow objects move. Whether it's a falling ball, a racing car, or even a rocket launching into space. In mechanics, time is like the backdrop for motion. Every movement, every change in position happens over time. Without knowing time, we can't describe how fast an object moves, or how its speed changes. Think about it. Speed, it's distance over change in time. Or velocity, it's displacement over change in time. Acceleration, it's how much velocity changes per unit of time. So, whether you're timing a race or calculating freefall, time is always in the equation. So in mechanics, motion is never complete without time. It's the constant factor that ties everything, from forces to motion, together. Next up, mass. We all know it as the amount of matter something has. But in mechanics, it means a whole lot more. Mass measures how much matter an object contains. But here's the key. In mechanics, mass tells us how an object reacts when a force is applied. Push a light ball, it moves easily. Push a heavy rock, it barely moves. Why? The heavier the mass, the harder it is to move. Mass is also tied to inertia, that natural tendency of objects to resist changes in their motion. An object at rest wants to stay at rest. And an object in motion wants to keep moving, all because of mass. That's why it's harder to stop a moving truck than a moving bicycle. More mass means more resistance to change in motion. Don't worry, we'll talk more about inertia later on. So in mechanics, mass isn't just about size or weight. It's the measure of how much an object resists movement. And it plays a huge role in every motion and force calculation. And finally, let's talk about one of the most important players in mechanics, force. What exactly is it? A force is any push, pull, or interaction that can cause an object to move, stop, or change direction. It can come from direct contact, like when you push a door open, or act at a distance, like gravity pulling objects toward the earth, or magnets attracting metal. In mechanics, we don't just say a force happens. We describe a force using 3 key things. Point of application. Where exactly is the force applied on the object? Magnitude. How strong is the force? Direction. Where's the force pushing or pulling? Because of these 3 characteristics, a force isn't just a number, it's a vector. That means it has both magnitude and direction, making it essential for solving problems in engineering and physics. So, let's review. Space tells us where. Time tells us when. Mass tells us how much matter and resistance. Force tells us what causes change. These 4 basic ideas are the heart of mechanics, and together they help us describe, predict, and control motion in the real world. Now let's talk about a key idea in Newtonian mechanics. Why are space, time, and mass considered absolute? And why is force the special one that ties everything together? In Newtonian mechanics, space is absolute. It's like a giant invisible stage where everything happens. Objects move, forces act, but the stage itself doesn't change. Time is absolute. Whether you're standing still or traveling fast, time ticks at the same rate for everyone, like a universal clock. Mass is absolute. An object's mass doesn't change, no matter where it is or how fast it's moving. These three, space, time, and mass, are treated as fixed, unchanging foundations of classical physics. But force? That's a different story. Force is directly tied to mass and how motion changes over time. This is the heart of Newton's second law of motion, the famous equation force is equal to mass times acceleration, which is how quickly the velocity of an object changes over time. Let's say you push an empty shopping cart. It moves easily. But load it with heavy groceries, you need more force to make it move at the same speed. Why? Because mass resists motion. The greater the mass, the more force you need for the same acceleration. And if you want that cart to move faster, that's acceleration. You also need more force. This simple relationship, force, mass, and acceleration, is at the core of how engineers design machines, vehicles, buildings, and even rockets. It explains why bigger engines are needed for heavier cars, why we need stronger brakes for trucks, and why understanding motion is critical in almost every field of science and engineering. Don't worry, we'll talk more about law of acceleration later on. Now, you might have heard, in Einstein's theory of relativity, space, time, and even mass aren't absolute anymore. It showed us where Newton's laws reach their limits, especially in extreme cases like high speeds or massive gravitational fields. But here's the truth. For everyday engineering and mechanics, Newtonian principles still hold strong. They're the reliable tools we use when dealing with structures, machines, and motion in our world. So remember, space, time, and mass are the fixed stage and characters. But force is the action that makes everything move. That's why understanding force is the key to mastering mechanics. Now let's break down two of the most important ideas in mechanics, particles and rigid bodies. Why do we study them? And how do they help engineers solve problems in the real world? First up, particles. In mechanics, a particle is not literally an atom or a molecule. It's any object that we treat as if it has mass but no size or shape, just a single point in space. Why do we do that? Because sometimes we're only concerned about an object's motion or position, not its size. For example, when studying how a satellite orbits the Earth, we can simplify the satellite as a particle. This makes analyzing its motion much easier. Next, rigid bodies. A rigid body is made up of many particles, but with one key difference. The particles are fixed in position relative to each other. This means that even when the rigid body moves or rotates, the distance between any 2 points on it never changes. Think of a car. It doesn't deform or change shape when we apply forces. At least, that's our ideal assumption in basic mechanics. Why is this important? Because almost every object we analyze in engineering, from machines to buildings, can be modeled as either a particle or a rigid body depending on the situation. Need to study motion in space? Treat it like a particle. Need to analyze forces, stability, or rotation? Model it as a rigid body. For example, analyzing a falling ball, use particle mechanics to focus on motion. Designing a bridge, use rigid body mechanics to calculate stresses and supports. Understanding particles helps you understand the basics of motion. Understanding rigid bodies helps you build everything from machines to skyscrapers. So whether you're an engineering student, a physics enthusiast, or just curious, remember, particles simplify motion. Rigid bodies simplify structure. Master these, and you'll have a solid foundation in mechanics. Now, we're diving into the 6 fundamental principles of mechanics, essential concepts that every engineer and physics student needs to understand. And yes, these principles aren't just theories. They're backed by experimental evidence. Let's dive right in. First, the parallelogram law, or the parallelogram law of vector addition. When two forces act on a particle, we can replace them with a single force, called the resultant, by drawing a parallelogram. The two forces become adjacent sides, and the diagonal represents the resultant force. This principle helps us simplify complex force systems into one manageable force. Second, the principle of transmissibility. On a rigid body, you can move a force anywhere along its line of action, and it will have the same external effect on the body. This is why, in statics, engineers shift forces to points that make analysis easier, like at supports or joints. So we know the principle of transmissibility. You can move a force anywhere along its line of action on a rigid body, and it'll have the same external effect. But does this always work? Let's break down its limitations. First, it applies only to rigid bodies. The principle assumes the body doesn't deform. But if the body is deformable, like soft materials or flexible structures, moving the force may change internal stresses and strains. Second, it's valid only for external effects. It works for analyzing overall force balance or motion. But it won't guarantee the same internal force distribution. And that's a big deal when you're checking for strength or deformation inside a structure. Third, it's not applicable in deformable body mechanics or strength of materials. For example, in beams, moving a force along its line of action can change the shear forces and bending moments at specific points. So remember, the principle of transmissibility works great for rigid body equilibrium and motion. But when you're dealing with deformation, stress, or internal forces, you can't just move the force around. It's a different story. Third, Newton's first law, also called the law of inertia. If the net force acting on a particle is zero, it will either stay at rest or move in a straight line at constant speed. No force, no change in motion. This explains why objects don't just start moving on their own. Like a ball on the ground, it won't move until you kick it. Fourth, Newton's second law, also called the law of acceleration. This is the famous force equals mass times acceleration equation. If a net force acts on a particle, it accelerates in the direction of that force. The bigger the force, the bigger the acceleration. But the bigger the mass, the smaller the acceleration for the same force. It's the law that powers everything from car engines to rocket launches. Fifth, Newton's third law of motion, also called the law of action and reaction. For every action, there's an equal and opposite reaction. Push on a wall. It pushes back with the same force. Hit a nail with a hammer. The nail pushes back on the hammer with equal force. Forces always come in pairs. And sixth, Newton's law of universal gravitation. It explains not just why apples fall, but also why the planets stay in orbit and how gravity affects everything in the universe. Newton's law of gravitation tells us that any two objects, one with mass big M and the other with mass small m, will always attract each other with equal and opposite forces. Now, you'll see different notations in textbooks. Some use big M and small m, while others write m sub 1 and m sub 2, but it all means the same thing. Any two masses in the universe will pull on each other, no exceptions. And the magnitude of that force is given by this formula. The force of attraction is equal to the gravitational constant, times the product of the masses of the two objects, divided by the square of the distance between their centers. And since these forces are equal in magnitude, often labeled as F sub 1 and F sub 2, we usually just write it as F because the size of the force is the same for both objects. This law also brings in a cool concept, action at a distance. Even if two objects aren't touching, they still pull on each other with equal and opposite forces. This idea also extends Newton's third law. The action force and reaction force are equal in magnitude, opposite in direction, and along the same line of action. Now let's talk about a special case. The attraction between the Earth and an object on its surface. Here, m sub 1 is the mass of the Earth, m sub 2 is the mass of the object, and r is the radius of the Earth. By simplifying the equation according to Newton's second law, force is equal to mass times acceleration. If the force acting on a small object m sub 2 is gravity alone, you can cancel m sub 2 on both sides. Then we get gravitational acceleration is equal to the universal gravitational constant times the mass m sub 1 of the planet or celestial body divided by the square of the radius from the center of the mass to the point of measurement. This equation is also called the formula for gravitational field strength at the surface of a planet or celestial body. In some references, m sub 1 is written as a capital letter M to represent the mass of the planet, and small letter r is written as a capital letter R to represent the radius from the center of the mass to the point of measurement. But it all means the same thing. This tells you how strong gravity is at a distance r from a mass m. On Earth's surface, this gives gravitational acceleration g is approximately equal to 9.81 meters per square second. In short, Newton's universal gravitation gives you the gravitational force between two masses. When you apply Newton's second law, you see that gravity causes an acceleration. That's the gravitational acceleration g we experience on a planet's surface. That's why the equation for the gravitational acceleration comes directly from Newton's universal gravitation plus Newton's second law. And this is where we get the formula for weight, the force Earth exerts on an object. Weight is equal to mass times the acceleration due to gravity. So your weight isn't just a random number, it's actually the gravitational force acting on your mass. Does gravitational acceleration change? Yes, slightly. Because the Earth isn't a perfect sphere and its rotation affects gravity, gravitational acceleration varies depending on your location. But for most engineering calculations, we assume gravitational acceleration is equal to 9.81 meters per square second. This is in the SI, or International System of Units, also known as the metric system. Please note that the term SI comes from the French phrase
Système international d'unité.
And in the imperial or U.S. customary system, gravitational acceleration is equal to 32.2 feet per square second. That's accurate enough for most real-world applications. So next time you think about gravity, remember, it's not just about falling objects. It's a universal force acting between all masses everywhere. And it's one of the key principles behind both physics and engineering. These 6 principles form the backbone of mechanics. So now that we've explored the 6 fundamental principles of mechanics, you might be wondering, when and how do we actually use all these? In your study of mechanics, we won't throw all these principles at you at once. We'll bring them in when they're needed, step by step. For statics of particles, we'll mostly rely on the parallelogram law and Newton's first law. That's where you'll start. When we move on to the statics of rigid bodies, we'll introduce the principle of transmissibility. It helps us simplify force systems on solid structures. As we study how forces interact inside structures, like beams or trusses, Newton's third law will come into play. That's action and reaction at work. And when we dive into dynamics, where motion really happens, we'll bring in Newton's second law and the law of universal gravitation to explain how things move under force. Over time, you'll see how some principles are connected. For example, Newton's first law is actually a special case of Newton's second law when the net force is 0. And even the principle of transmissibility can eventually be derived from other laws once you master the bigger picture. Laws such as Newton's laws of motion, equilibrium conditions in statics, moment of a force, and rigid body assumption. These principles aren't just textbook theories. For over 2 centuries, engineers have used them to solve real-world problems. From analyzing the forces in bridges, to predicting the motion of vehicles, to designing systems in aerospace and machinery. And because these principles are grounded in experimental evidence, many of the solutions we get have been tested and proven in the real world. So as we move forward in this series, keep these 6 fundamental principles in mind. They're your foundation, your blueprint, for understanding both the science and the art of mechanics. If you found this video helpful, hit that like button, subscribe for more engineering insights, and don't forget to drop your questions in the comments below. I hope you learned something new today, and I'll see you on the next one. Bye.